So in this video I'm going to do some more examples of phase lines and just kind of what we get from them. So, and also just I wanted to show a little bit kind of the limitations of them. So we'll just jump right into it. So for example, if I have dy dx is equal to 1 plus y squared. So again, to write a phase line, the first thing we do is look for equilibrium points. And we notice that when y equals 0, we have an equilibrium point. Equilibrium point. So if we were to draw our phase line, we'll put a dot at y equals, I don't know why I just said 0, that was weird. Y equals -1 is what I meant to say. Y equals -1. And then we look at the graph and we notice, I'm sorry, we look at this, the f of y. Oh, first up, let's back up a second. We notice, first of all, that this is just in terms of y, which means that enables us to use a phase line. Remember we talked about that we can only use a phase line because when the differential equation is, the right side of the differential equation is only in terms of y, then we know on the slope field that all the slopes in one horizontal line are going to be the same, and that's what enables us to use a phase line, because the phase line kind of represents, if we know what's happening at each stop along the y-axis, we know what's happening to the right and the left of it. Okay, so then the next thing we notice is that this expression right here will always be positive because of the squared. So if I'm above the equilibrium point, the rope climber will be going up, remember, because the slope, the derivative is positive. So remember, this is how fast he's moving, and velocity, positive means going up, negative means going down. So in both cases, if you start out below the equilibrium point, you will be going up. Okay? So, and if we were to sketch what this looks like, remember what the phase line does for us is we know that there's a horizontal line at the equilibrium point. And basically, if we start out above the equilibrium point, you're going to be going up. So if we pick some point like here, we know it's going to go up. Now, we don't know how fast it's going to go up, but the general rule is that the closer you get to a horizontal equilibrium point, the slower you go, and the further you get away from, the faster you go. So in this case, if we go forward, it's going to head up, and as we go backwards, it's going to go closer and closer. Likewise, if I start somewhere over here, it's going to go, if I start somewhere like anywhere in here, it's going to go up, but it'll slow down as it gets closer and closer. It doesn't turn around and go back down. If I start right here, let's say, it'll slow down as it gets closer and closer, and as we go the other way, it will shoot off into space. Okay? So those are a couple examples. Now, so this is the phase line, and this is roughly what it tells us. So we look at this, and what we can establish from this, if my y sub 0, or my initial condition, is greater than -1, so above the equilibrium point, then we see that y of t heads towards positive infinity as t approaches positive infinity. Oh, whoops, I used x in this. My bad. Make sure you're as x approaches infinity. Okay? And if y of 0 is less than -1, then y of t approaches the equilibrium line, the equilibrium solution, or approaches the horizontal line at y equals -1 as I used t again, sorry folks, as x approaches infinity. Now we know that it never gets there. There's a horizontal asymptote there, but it is approaching. So, but we don't really know how fast it's approaching infinity, or whether you have to get closer and closer to whether x, how far x we have to go out the x-axis to see the approach to infinity. Really what we come down to is there some vertical asymptote in here which is going to cause us to go to infinity at a finite value of x, or does it just, as we go out the x-axis, it just gets bigger and bigger? So the question is, does this approach infinity at a finite number, or does it take all of x to approach infinity? And we can't tell that from the phase line. So if we look at this for a second, we notice that dy dx actually is obviously a separable equation. So we could rewrite this as dy over y plus 1 plus y squared is equal to dx. And if we integrate that, so now we're going for an analytical solution using the separation of variables. And if we integrate this side, we end up with what? Negative 1 plus y to the negative 1. And over here we get t plus c. And that would give me, 1 plus y is equal to negative 1 over t plus c. And therefore y is equal to negative 1 minus 1 over t plus c. Now, what we notice here, now that we're looking at the general form of the solutions for this differential equation, we realize that, well, not knowing what c is yet, but we realize that if you recognize this from pre-cal, this is a rational function, and we know that this thing is going to have a vertical asymptote, vertical asymptote at, I'm putting the t in there again, guys. I got used to using t's. Sorry about this. At vertical asymptote at x equals negative c. So this, obviously this tells us more than the phase line does. We knew from the phase line that it is headed towards infinity. We just didn't know whether it was going to take infinity to get there, or whether it was going to head towards infinity at some finite value of x. And so when we use separation of variables and come up with a general solution of the equation, we discover, now we know that it actually does head towards infinity for some finite value of x, and specifically at negative c. So anyway, that's a little, gives you an idea of I guess the ability of phase lines, but also the shortcomings. The other thing I want to talk about is we could be given, so let's say we have this dy dx is equal to, there's another differential equation, f of y, but they don't tell us what f of y is, but instead we get a picture. And the picture looks something like this. So this is a graph of f of y, where that's the y function and that's the f of y. I'm sorry, that's the y-axis and that's the f of y-axis. Okay, and let's say that that point right there is A, that point right there is B, and that point right there is C. So remember, first thing we do is look for equilibrium points, and the equilibrium points are what make the right side of the expression 0. So we know that we have equilibrium points at A, B, and C. So when I go to draw my phase line, I'm going to put a dot at y equals A, a dot at y equals B, and a dot at y equals C. And then the next step is to figure out whether this thing is going up or down. So remember, this is describing When the derivative is positive, the guy's going to climb up the rope. When the derivative is negative, he's going to climb down the rope. So we can tell that before a or below a, the derivative or the right side of the expression was positive, so that means he's climbing up. And then between a and b, the f of y is negative, so that means he's climbing down. And then between b and c, the f of y is positive again, so that again tells me he's climbing up. And then finally, after c, it's negative, so that means he's climbing down. Okay? So again, we just need some kind of information about the right side of the differential equation, and whether we give it to us in equation form, or if they just give us a graph of it, we can come up with a phase line. And again, once we've drawn this phase line, you could possibly sketch some solutions from this. You know, there's going to be a horizontal line right there, horizontal line right there, and a horizontal line right there. And we know that between B and A, it's always going down, so that gives me the impression of something possibly like that, or like that. Below A, it's going up, so we would picture something like this possibly. And between B and C, it's going up, so that envisions something kind of like this. And above C, something coming down. Now remember, what I mean by below C or above C or between A and B, we're talking about where the initial condition is. So if they say, for example, if they say, for example, that the initial condition is y of 0 is equal to, I don't know, D, and D happens to be right here, right? That means I would be starting right here, and I know well, not right, but right there, I know, I didn't put a y-axis in here, but you know what I mean. I'd be starting here, and I know that I'm going to go down from there as I get close to this, and going up as I go the other way. So that's what I mean by where we're at between them, is what the initial condition is. Okay? So there's a couple examples. I want to talk about, we have names for equilibrium points based on the behavior around them, and so I'm just going to throw them up here real quick. So we have something called a sink, something called a source, and something called a node. And basically, a sink is makes you think of like a kitchen sink. If you pour something in the kitchen sink. Actually, here's a sink right in here. Look at this. Check it out. See that sink? So if I turn the water on, everything goes down the drain, right? So, so that gives you this impression, hopefully, that a sink is, everything is headed towards that equilibrium point. So we would, if we're looking at a phase line, we would expect it to look like this. So below the equilibrium point, the rope climber is climbing up. Above the equilibrium point, the rope climber is climbing down. So we call that a sink. A source is the opposite, because it's, you think of like the source of where something's coming from. So a source on a phase line, the arrows essentially are pointing away from it. So below the equilibrium point, the rope climber is climbing down. Above the equilibrium point, the rope climber is climbing up. And then finally a node, you probably have already guessed this if you've been paying attention, that they're going in the same direction. In other words, we can't tell. So it could look like this, or it could look like this. So they're not, in the sink and source, they're both doing the same thing as in respect to going away from each other or going towards each other. Well, I guess I could say, actually, it'd probably be better to say, if you look at these, the sink and source are doing the opposite of each other, whereas the node, they're doing the same thing. And in the node, they're either both going up on either side of the equilibrium point, or they're both going down. But I don't know. I don't think that's the best way to say. It's better to think of the sink is everything's going towards it, the source, everything's going away from it, and then the node is the other ones. So, and just to draw a picture of what this looks like, right? If we have an equilibrium point and everything's coming towards it, then you get a picture of something like this. Like multiple solutions are coming in like that. Everything's headed down towards the equilibrium point. If you have a source, then it's like things are coming out of it, right? No matter which way you're going, as you go to the right, things are going out of it. And then finally, with a node, you have something coming in from top. Let's see. And maybe going out like this. So here it's sinking towards it, now it's going away from it, or the other way around. So